Hi, I'm Abhraneel. I'm a PhD student at Northwestern, and I'm going to be talking about our paper Odds and Insights, Decision Quality and Exploratory Data Analysis Under Uncertainty. This is work done with my co-authors Xiaoying, Yuan, Michael Correll, Eli Brown, and Matt Kay. In this paper, we try to answer the question, how concerned should we be about false discoveries in exploratory data analysis? Before I talk about what we did in this paper, we do need to establish a few preliminaries. Imagine that there is a company which operates stores in 16 different regions. In each of these 16 regions, they operate 200 stores. Now, assume that you are an analyst for this company and you have the data from 20 out of 200 stores from a region. You're asked to determine whether the stores in this region are profitable or not on average. Well, you're eventually going to find out whether this region was profitable or not. How would you make this determination based on the currently available information? Such tasks are not too dissimilar to those performed in typical EDA scenarios. If you're like me, you would probably try to perform this task by visually estimating the mean of the dots shown here. Based on this information, you might reasonably conclude that the stores in this region are likely profitable on average. Now let us add another layer to this problem. Because you're a high-level employee of this company, your yearly bonus is directly tied to the company's profits. Based on past data, you have been able to determine that if your analysis determines a region to be profitable, and the region is actually profitable, that is, your decision is a true positive, your bonus increases by $5,000. However, if the region is not profitable, that is, your decision is a false positive, your bonus will get reduced by $195,000. Similarly, if your analysis determines a region to be not profitable, but the region is actually profitable, your bonus will go down by $4,000. And for every true negative decision, your bonus increases by $1,000. Going back to the question of profitability, will you still say that the stores in this region are profitable on average? Let us examine this scenario more closely. Under the current incentive structure, the cost of one false positive is the same as the gain from 39 true positives. Thus, we can define the false discovery rate, which is the ratio of the total number of false positives, to the total number of discoveries, which is false positives plus true positives. In order to optimize for this incentive structure, we need the false discovery rate to be less than 0.025. Now, in order to make an optimal decision, I would first estimate the mean. Then I would draw a 95% confidence interval. This confidence interval expresses the uncertainty in our estimates of the mean. In other words, if I draw a 95% confidence interval when performing many such tasks, we can expect 95% of those intervals to contain the mean. And as a result, I would be correct 95% of the time. In this case, adopting such a strategy, where the 95% confidence interval overlaps or does not overlap 0, would allow an analyst to optimize for this incentive structure. Now we can establish our first preliminary, which is if we want people to make good decisions under uncertainty, we need to provide them with appropriate uncertainty visualizations, as not providing them uncertainty visualizations make the task incredibly difficult to the extent that they may not be able to perform it. We can put the first preliminary away and return to our task. Here, we see that 95% confidence interval overlaps 0. Thus, in this scenario, we should not consider this region to be profitable on average. However, what if I were to change the incentive structure such that the cost ratio of true positives to false positive is 9:1? In such a situation, we can use an 80% confidence interval. Here we see that the conclusions would have changed. Under this incentive structure, we would conclude that the region is profitable on average. Similarly, if the cost ratio was 3:1, we can use a 50% confidence interval. This was the incentive structure that we used in our study. You may have realized that what we are doing just now is essentially null hypothesis significance testing at different alpha levels. Thus, we are ready to establish our second preliminary. In order to determine whether a decision under uncertainty is correct or incorrect, we need an explicit incentive structure. Let us tuck this preliminary away and return to the company which operates stores in 16 different regions. Now, what if I ask you whether the stores are profitable or not in a second region? How about for each of the other 14 regions? You may be able to visually estimate the means. You might even be able to visualize an approximate confidence interval in your mind. Based on this, you might say that these are the regions which are profitable on average. But would you still be correct? Sadly, no. This is because as the number of comparisons increases, so does the probability of a false discovery. Additionally, in this scenario, the expected false discovery rate is 0.45, which is no longer optimized for the incentive structure that we are trying to optimize for. Many of you may have realized that this is simply the multiple comparisons problem, according to which, as the number of comparisons increases, so does the probability of making a false discovery. This means without correcting for multiple comparisons, you cannot ensure that your false discovery rate is controlled for at a selected alpha value. So our final preliminary is that exploratory data analysis, where users iteratively explore different facets of the data, involve making multiple comparisons. Now, keeping this preliminary in mind, let us return to the original question. So how concerned should we be about false discoveries due to the multiple comparisons problem in exploratory data analysis? Well, Zagragan et al. Conducted an experiment where they gave people a dataset that is mostly Gaussian noise, but with a few genuine correlations in it. They let people generate as many graphs as they wanted and recorded the subsequent insights. On each page, participants were presented with either 12, 16, or 20 graphs. This was varied within subjects. We varied the way the information was presented between subjects. Participants saw either a scatter plot, a confidence interval, or a density plot of the sampling distribution of the mean. And participants were provided with a very similar incentive scheme as the one from earlier in the presentation. I would like to add that designing this experiment and determining an appropriate incentive scheme was particularly challenging, as we needed to ensure that there was sufficient signal for us to distinguish between different strategies that people might be using. You can find more details about this in the paper. In each trial, we informed participants what their cumulative payoff was. Based on the participant's decision in every trial, we can calculate the total number of true positives, false positives, true negatives, and false negatives. We then use a Bayesian multi-level multinomial regression model to calculate the posterior probability distributions of the average number of true positives, false positives, true negatives, and false negatives. We can use these posterior estimates to obtain a posterior average false discovery rate and compare participants' performance between conditions. Additionally, we can also use the payoff to compare participants' performances across conditions. Let us first compare false discovery rates. So we're trying to control for the false discovery rate at 0.25, given the incentive structure. The false discovery rate, if we were to use an uncorrected strategy for multiple comparisons, then we would be somewhere around here. And finally, the false discovery rate using a correction procedure known as the Benjamin-Hochberg method, which is state-of-the-art, would result in a false discovery rate around here. So the average participant in the baseline scatter plot condition actually performs worse than the uncorrected strategy. This is not surprising, as the visualization is suboptimal for this task. However, the average participant in the confidence interval and the density conditions performs slightly better than the uncorrected strategy. However, despite these improvements, the average participant will likely not be able to control for false discoveries at the desired alpha level. We also collected qualitative responses from participants describing the strategies that they were using. Several participants reported using a Bonferroni-like correction method. For instance, one participant reported adding to the length of the bars to be more conservative in their decisions. Another reported shifting their decision criteria based on the area under the zero line of the density plot. We also observed certain learning effects. Consider this participant who made the following quote. The full quote reveals that they adapted their strategy to become more conservative as they progressed through their trials. Specifically, while they initially marked regions as profitable if 25% of the area under the bell curve was under the zero line, they adapted their strategy to be more conservative. When it comes to payoff, adopting an uncorrected strategy actually leads to a negative payoff. while a Benjamin-Hochberg strategy would result in a small positive payoff. In addition, we define the payoff based on a mean strategy corresponding to making decisions based only on the mean of the visualized data. Now, in the baseline condition, this is what the payoffs look like. We observed that 80% of the participants in these conditions performed worse than the uncorrected strategy. Even in the confidence intervals and density conditions, several participants actually performed worse in the uncorrected strategy. More promisingly, however, there was a significant proportion of participants in these conditions who were able to optimize for the given incentive scheme and ended up with a payoff which is very close to the Benjamin-Hochberg strategy. The first takeaway I wanted to highlight from our study is that incentives are necessary to study decision making. In the absence of explicit incentives, demand characteristics might lead participants to believe that the experimenter wants them to maximize the total number of discoveries without regarding for the correctness of their discovery. Thus, the absence of explicit incentives does not necessarily mean that participants in such studies are not using any incentives when performing the task. Second, we need to provide people with the right tools for the task. We can't expect them to be making a house if we only give them cardboard instead of wood. In decision-making tasks, uncertainty visualizations are absolutely necessary. Finally, given the right tools for the job, we observed that most participants performed better than an uncorrected strategy. Things might not be as bleak as prior work may have suggested. Some participants even perform as well as state-of-the-art procedures such as the Benjamin-Hochberg. We believe, moreover, that this gap can be closed through proper training. Thank you.